Swayam Prabha. Digital India. Educated India.
Welcome to the 28th lecture in Mechanics of Materials. Till now we have solved two kinds of boundary value problems. One involving an axial member wherein the axial stresses were uniformly distributed across the cross section. The second was a beam problem, bending problems, wherein we had both the axial stresses and shear stresses coming in the cross section. We saw how to compute the axial stresses in the cross section, which will vary linearly across the depth of the cross section. And then we saw that the shear stresses will vary parabolically across the depth of the cross section for certain types of cross sections. Okay, so basically now we'll move on from bending problems to twisting problems, wherein we saw even in bending problems that there will be a torsional moment or twisting happening in the cross section. The load is not applied through the shear center of the cross section, right? Okay, so now we look at what happens when the load is not applied to the shear center of the cross section or when there is twisting. We won't go into the specific case of load not being applied to the shear center, but we'll look at problems, simple problems in twisting where you have a shaft which is rotating at some RPM, or you are applying a twisting moment to a beam due to eccentrically applied load and so on. Okay, now in contrast to what we have been seeing till now, wherein the predominant stresses were the axial stresses, now the predominant stresses are the shear stresses in the cross in the structure. Okay, now due to twisting, what happens is you have a bar which you twist by applying twisting moment at one end, so you can see it forms kind of an ellipse kind of a shape here. Okay, so this is what happens when you apply a twisting moment to a bar. Okay, that is, I am fixing this end and I am rotating this section, and then this bar is getting twisted. Okay, so what happens now is two sections which are like this rotates related to each other. Okay, two sections which are like this rotates related to each other, producing a shear stresses in the plane of the cross section, and we are interested in finding what these shear stresses are in the plane of the cross section. Okay, now to analyze this, I am going to now change the coordinate system from what I have been using till now to a different coordinate system. This is just to make you conversant that any coordinate system that you use, you have to be able to adapt to a different coordinate system in a problem. Okay, so till now we have been using XYZ orient in a particular fashion, but now I will orient the XYZ in a different manner. Okay, I have this cross section, and for me now Z is the axis of the beam, Y still remains the vertical, but X is oriented like this. Okay, so this is the axis that I am going to use. Now what was the torsional moment in case of the axis oriented, like when the X was oriented along the axis of the beam, the moment along X direction was the torsional moment, and moment along Z direction was the bending moment. On the other hand, now the moment along the Z axis is the torsional moment, and moment along the X axis is the bending moment. Okay, now we have to find the expression for the torsional moment when the orientation is like this. So as I did before for the bending moment, I cut a section, expose the traction along the Z direction, and find what is the torsional moment. Okay, so now T's of EZ, I am not going to go into step by step procedure. You have to refer back to our first lecture in beam bending where we did this with respect to X to get this expressions. TEZ will be given by sigma XZ EX, YZ EY plus sigma ZZ EZ. Okay, now at a given cross section I want to find the moment due to this exposed traction. So the moment equation would be R cross T's of EZ integrated over dA. dAz now, because AZ is the Z is the axis of the beam. Okay, so now in this case R would be, now it will be AZ, R would be XCX plus YEY. I am not bothered about Z in this case because I am interested only in the torsion moment. Okay, otherwise I would have plus Z naught EZ, okay, cross sigma XZ EX plus sigma YZ EY, and I am also going to ignore sigma ZZ EZ because I am not interested in the axial stresses either. Okay, I assume there are no axial stresses in this case, dAz. So this will be integral x sigma yz minus y sigma xz dAz az ez. This is the torsional moment, mz moment. This is the torsional moment, or this is the torsional moment in the beam. Okay, now let's assume that I fix this end for torsion and I am applying a torsional moment T here. Okay, the double arrow indicates the torsional moment. Okay, when applying a torsional moment T in there, and I am interested in finding what will be the stress distribution in this structure. Okay, now as always what we do is start with the displacement field. We start with the displacement field, use the strain displacement relationship to get the strain, use the constellation to get the stress, equilibrium equations to get the forces or moments or whatever unknown displacement component that we add. Okay, so to assume a displacement field, we have to hypothesize on a possible mode of displacement. Okay, so towards that what we are going to do is we are going to see what happens when I twist a bar. Okay, so when I twist a bar and I fix this end and I twist the bar like this, apply a torque T like that, then what happens to a straight line here? What happens to the straight line there? Okay, this straight line is now going to deform into an inclined line, essentially an inclined line, because I am assuming the displacements are small. We saw that when we derive the strain, we always assume that the component of displacement is small, displacement gradient is small, so that I can do whatever I am doing, right? I can use a linearized strain measure to do the calculations. So since the displacements are small, unlike what I showed in the beginning of this lecture where the displacements were large, where you could see the displacements, now you can't see the displacement, and hence when the displacements are small, you can assume that the straight line deforms into another straight line like that, okay, which is inclined. Basically, since it is fixed at the end A, that end won't rotate. The section which is farther away from the fixed end will rotate more and more as the length increases. Okay, so basically let's assume that this rotation is given by omega. Okay, let that rotation be alpha. Then at any section, this rotation of the cross section from here to here would be, this rotation would be alpha times z. Again I am assuming that the rotation is small, so I can write this as alpha times z. Okay, because my axis is again oriented along, this is the z distance. My axis of the beam is oriented along the z axis. Okay, this is the z distance, so that will be alpha times z. Now let's look at the cross section. What happens? I have some arbitrary cross section. Okay, I have x and y in the cross section. This is the surface of the cross section, what you see as the elevation. So basically what happens to a line element, this line element is, it rotates, goes in there, okay, where this rotation is alpha times z, okay, and if this angle were to be beta, okay, this angle were to be beta, and if this radial distance were to be capital R, if this distance were to be capital R, then beta times R, capital R, should be equal to alpha times Z, right? Okay. Now then beta would be alpha by R into Z. Okay. This alpha by R is called, we will replace that symbol as omega Z, and this alpha is called as angle of twist per unit length. Okay. Now this is what has happened in the process. What has happened is a point which is here, a point which is here has moved to a point here, has moved to a point there. So it has a ux displacement and it has a uy displacement, which we have to find. Okay. Again, since beta is small, I wrote it as beta times r, which means this distance is beta times r. Okay. So I know that this distance is any point interior also would be beta times r. This some point in here, which is a distance of r, small r. Okay. So that will be that displacement. Okay. Now that displacement I have to resolve into ux and uy displacement. Basically, by assuming this displacement as beta times r, I am approximating the arc of a circle to the secant length, the arc length to the secant length. Okay. So now I am interested in finding this distance and this distance, and what I know is, I know that this makes an angle theta and this distance is r. Okay. If that distance is r and this is 90 degrees, I know this is 90 degrees. Okay. Then I can say that this angle would be theta, right? Because this angle is theta, this angle is theta by parallel lines. Okay. And this angle will be 90 minus theta and that angle will be theta. Okay. So this distance here would be given by beta r into cos of theta, right? And this distance here would be given by beta r into sine of theta. Okay. Now, so ux component or displacement, that is a negative displacement, it moves opposite to the orientation of the axis, hence it is minus beta r sine theta, or this is minus omega z. R sine theta is nothing but y, r sine theta is this distance y. Okay. So that is minus omega z y. Similarly, uy displacement is given by beta r cos theta. This is a positive displacement because it is displacing along the direction of the coordinate system. Okay. And this will be omega z, substituting for beta, and r cos theta is nothing but x. Okay. R cos theta is nothing but x. This distance is x and this distance is y, and hence that is what you got as ux and uy displacement. Okay. You are assuming that there is no displacement along the z direction, uz is 0, because I am assuming that there is no warping essentially. Okay. What I am assuming is there is no warping or there is no out of plane displacement, and hence uz is 0. Putting all this together, you get your displacement field u to be minus omega z y ex plus omega z x ey. Okay. Because you assume no warping. In other sense, what you are doing is you are deriving an equation for what is called as a closed section. Okay. Assuming closed section implying no warping.